The cosmos, an infinite expanse, holds secrets not just in its present vastness, but in its profound past. The very fabric of space itself appears to possess an intrinsic memory, an enduring record of every event that has ever transpired within its boundless embrace. From the colossal birth of galaxies to the delicate dance of subatomic particles, every moment leaves an indelible imprint. We observe the universe not as it is now, but as it was, a magnificent cosmic echo across the unimaginable corridors of time and distance. The fundamental principle behind space's memory lies in the finite speed of light. When we gaze upon a star, especially one millions of light-years away, the light reaching our eyes today embarked on its journey millions of years ago. We are literally looking into the past, witnessing the star as it existed when dinosaurs roamed the Earth, or even before humanity emerged. This cosmic delay transforms every observation into an archaeological dig through time. Consider a supernova, a dying star's explosive farewell. If such an event occurred in a galaxy 60 million light-years away, we would only witness its brilliant demise today, 60 million years after it actually happened. The light from that cosmic catastrophe has been traveling through the void ever since, carrying the tale of its spectacular end to us, a direct visual memory etched into the very light itself, bridging immense gaps in both space and time. This means that astronomy is inherently a historical science. Every single observation, every gathered photon, is a direct portal to a bygone era. The farther we look, the deeper into the past we delve. What appears as a shimmering point of light might be a galaxy in its infancy, or a star whose very existence ceased eons ago, its final light still relentlessly traversing the universe to share its ancient story with us. Scientists conceptualize this phenomenon using light cones, which illustrate the past and future events that can influence or be influenced by an observer at a specific point in space-time. Everything within our past light cone represents events whose light has had time to reach us. It's a cosmic archive, where the universe continuously broadcasts its history across the fabric of space-time, allowing us to reconstruct its epic journey. The oldest stars, known as population 3 stars, are theoretical entities, never directly observed. Their light, if we could see it, originated at a time when the universe was barely a few 100 million years old. These primordial giants forged the first heavy elements, seeding the cosmos for subsequent generations of stars and planets. Their fleeting existence is a crucial cosmic memory, recorded in the chemical composition of successor stars, quasars. Incredibly luminous active galactic nuclei represent another fascinating aspect of space's memory. These distant beacons are powered by supermassive black holes devouring vast amounts of matter. Because of their immense distance and brightness, they offer a glimpse into the conditions of the young universe, existing predominantly in epochs billions of years ago. Their light, a record of immense energy, traveled for eons to reach us. Each photon embarking on its journey across the cosmos is a tiny messenger, carrying information about the moment and place of its inception. It travels an unfathomable distance, navigating gravitational fields, dark matter filaments, and interstellar dust, often for billions of years, before finally reaching a detector or an eye. This makes every photon a relic, a silent testament to a fraction of a second from the universe's grand narrative, frozen in time. Modern telescopes, such as the James Webb Space Telescope and the Hubble Space Telescope, are our primary tools for reading these cosmic memories. They act as colossal time machines, gathering faint, ancient light, enabling astronomers to piece together the universe's autobiography. From the very first galaxies forming out of the primordial soup to the majestic spirals we see today, their images are indelible records of development. The sheer scale of cosmic time is almost beyond human comprehension. The universe is approximately 13.8 billion years old. Our Sun and solar system formed relatively recently, about 4.6 billion years ago. The first starlight, the earliest structures, all emerged in the universe's distant infancy, providing a profound historical dimension to every observation we make, pushing the boundaries of memory itself. In essence, the entire observable universe is a living, breathing historical record. It continuously expands, yet every expansion carries with it the imprints of previous states. The distribution of galaxies, the cosmic web's vast filaments, and even the emptiness of the voids all bear witness to the gravitational dance and energy fluctuations of billions of years past. Its current structure is a direct consequence of its ancient history. Every star's light is a silent message, a spectral fingerprint encoding its chemical composition, its temperature, its motion, and its age. When that light finally reaches Earth, it delivers not just illumination, but a detailed historical report. It tells us stories of supernova events that scattered heavy elements, of stellar nurseries where new suns were born, all preserved within the very photons carrying the information. Even the effects of gravitational lensing contribute to this cosmic memory. Acting like natural cosmic magnifiers and distortions, massive galaxy clusters bend and magnify the light from objects located behind them, often revealing incredibly distant, otherwise invisible galaxies. These distorted arcs and multiple images are not just optical illusions. They are indirect records of the mass distribution of foreground objects over vast swaths of cosmic history. The universe's memory is not static. It's a dynamic, ever-unfolding narrative. As new light arrives from ever more distant corners, our understanding of the past deepens. Future missions will continue to push the boundaries of observability, aiming to capture the earliest moments after the Big Bang, perhaps even revealing the light from population 3 stars, the very first suns that ignited in the cosmic dawn. The profound implication of space having a memory is that the past is never truly gone. It is merely transformed into information, encoded in the light, in the very geometry of space-time, and in the distribution of matter. Our universe is one giant continuous history book, perpetually being written and simultaneously being read by the curious minds capable of deciphering its ancient language, pushing the frontier of knowledge. One of the most compelling pieces of evidence for the universe's profound memory comes from the cosmic microwave background, or CMB. This faint, uniform glow of radiation permeates all of space, acting as a profound echo of the Big Bang itself. It's not just a relic, it's the direct image of the universe when it was a mere baby, only 380,000 years old. CMB represents the moment when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. Before this epoch, known as recombination, the universe was an opaque plasma, with photons constantly scattering off charged particles. Once atoms formed, light could travel freely, and this first light of the universe is what we detect as the CMB today, a direct witness to cosmic dawn. The accidental discovery of the CMB in 1964 by Arno Penzias and Robert Wilson while working on a new horn antenna for Bell Labs was a monumental moment. They kept detecting a persistent, mysterious static, initially dismissed as pigeon droppings. It was eventually identified as the uniform background radiation predicted by theoreticians, forever changing our understanding of the universe's origin. Often referred to as the baby picture of the universe, the CMB provides an unprecedented snapshot of its earliest moments. It reveals tiny temperature fluctuations, differences of only a few parts in 100,000, which are crucial. These minute variations were the primordial seeds, the tiny gravitational perturbations that would eventually grow over billions of years into the vast galaxies and clusters we observe today. This ancient light tells us that the universe, at 380,000 years old, was remarkably uniform, but not perfectly so. These imperfections, these tiny ripples in the cosmic fabric, are like fingerprints of primordial quantum fluctuations, stretched across the entire observable cosmos by rapid expansion. They are the initial conditions from which all complexity ultimately arose, the universe's very first memories of structure. The precise measurements of these CMB fluctuations, obtained by missions like COBE, WMAP, and Planck, have allowed cosmologists to determine fundamental parameters of the universe with astonishing accuracy. They have confirmed the age of the universe, the proportions of normal matter, and dark energy, and even the geometry of space-time. It is a treasure trove of information from the universe's earliest epochs. Without these tiny temperature variations in the CMB, the universe would be a featureless, homogeneous void. There would be no denser regions for gravity to pull together, no overdensities to attract more matter. These fluctuations were the gravitational seeds that later matured into the majestic galaxies, the sparkling star clusters, and the grand cosmic structures we marvel at, a memory of creation's blueprint. The patterns observed in the CMB also provide compelling evidence for cosmic inflation, a theoretical period of extremely rapid expansion just fractions of a second after the Big Bang. Inflation would have smoothed out the universe while simultaneously stretching quantum fluctuations to cosmic scales, imprinting them onto the CMB. This rapid expansion left an indelible mark, a memory of a truly explosive beginning. Dedicated space missions have meticulously mapped the CMB across the entire sky. The Cosmic Background Explorer, or COBE, confirmed its black-body spectrum. The Wilkinson Microwave Anisotropy Probe, or WMAP, provided higher resolution and precision. Most recently, the Planck satellite delivered the most detailed map to date, refining our cosmic parameters and deepening our understanding of the universe's fundamental story. The data from these CMB missions is not just numbers. It's a profound visual representation of the universe's earliest existence. Cosmologists translate the microwave signals into stunning all-sky maps, displaying the minute temperature differences as vibrant patterns of color. These maps are the closest humanity has ever come to seeing the universe in its infancy, a true historical document written in light. The CMB radiation, originally incredibly hot, has cooled dramatically over billions of years due to the universe's expansion. It now registers at a frigid 2.725 degrees Kelvin, just above absolute zero. This extreme cooling is another testament to the universe's memory, retaining the signature of its initial heat and expansion, even as it chills towards its ultimate destiny. The moment of decoupling, when matter and radiation separated, marked a pivotal point in cosmic history. Before this, matter and light were inextricably linked, forming a primordial plasma. After decoupling, photons were free to travel without hindrance, preserving the state of the universe at that precise instant. The CMB is therefore a direct relic of this significant event, carrying information from before the universe became transparent. The existence and characteristics of the cosmic microwave background serve as powerful validation for the Big Bang theory. It's not just a theoretical construct, it's an observable remnant, a direct piece of evidence supporting the universe's fiery beginning and its subsequent evolution. Without the CMB, our understanding of cosmic origins would be far more speculative. With it, we have a concrete memory of birth. The CMB also demonstrates the remarkable homogeneity and isotropy of the universe on large scales. Despite the tiny fluctuations, the universe is incredibly uniform in all directions, suggesting a common origin and evolution. This uniformity is a cosmic memory of the initial, highly ordered state of the universe, setting the stage for the structures we see today to emerge from subtle variations. The cosmic microwave background truly is the universe's oldest and most profound memory. It's a fossilized light imprinted with the conditions of our cosmos's infancy, providing insights into its very earliest moments. It is the ultimate historical record, constantly reminding us of our universe's humble yet explosive beginnings, and how far it has evolved over billions of years. Beyond light, space-time itself holds memory, manifest in the form of gravitational waves. These are ripples in the very fabric of space-time, much like waves on a pond, but far more profound. Generated by the most violent astronomical events, they carry information across the universe at the speed of light, providing a completely new way to hear the cosmos and its cataclysmic past. Albert Einstein predicted the existence of gravitational waves in 1915 as a consequence of his theory of general relativity. However, he believed they would be far too faint to ever detect. It took a century of theoretical development and groundbreaking engineering to finally prove him both right about their existence and wrong about their undetectability. Their discovery validated a cornerstone of modern physics. Gravitational waves are generated by massive objects accelerating rapidly, fundamentally altering the curvature of spacetime. The most powerful sources are cataclysmic events, the merging of two black holes, the collision of two neutron stars, or the explosive collapse of a massive star as a supernova. These cosmic ballets warp spacetime dramatically, creating ripples that propagate outwards for eons. Imagine spacetime as a vast, stretched rubber sheet. When a massive event occurs, it causes vibrations in this sheet, sending ripples across its surface. As these gravitational waves pass through Earth, they cause incredibly minute distortions, stretching and squeezing space itself by fractions of an atomic nucleus. It's this imperceptible distortion that detectors endeavor to measure, capturing a direct memory of distant cosmic violence. The breakthroughs in detecting these elusive ripples came with instruments like the Laser Interferometer Gravitational Wave Observatory, known as LIGO. This detector, with its colossal L-shaped arms extending 4 kilometers, uses precisely tuned lasers to measure minute changes in distance caused by passing gravitational waves. It's an engineering marvel designed to sense the faintest whisper from the depths of the universe. On September 14, 2015, LIGO made history with the first direct detection of gravitational waves. The signal, lasting only a fraction of a second, was the chirp of 2 massive black holes, 36 and 29 times the mass of our Sun respectively, spiraling inward and merging some 1.3 billion light-years away. This historic event revealed a new era in astronomy, a new memory channel. The information carried by gravitational waves is unique. Unlike light or neutrinos, gravitational waves interact very weakly with matter, meaning they travel almost unimpeded across the vastness of space. This grants us a pristine view of events that might otherwise be obscured by dust or gas, allowing us to peer directly into the heart of extreme cosmic phenomena, unearthing deeper memories of the universe. If gravitational waves had a sound, the detected chirp of merging black holes would accelerate in pitch as the objects drew closer, culminating in a powerful burst. It's a cosmic crescendo, literally a sound from the universe's most violent events, played out on the fabric of space-time itself. This allows us to listen to the universe's memory, giving us an auditory perspective beyond mere visual observation. The frequency and amplitude of gravitational waves encode precise details about their sources, the masses of the merging objects, their spins, and even their orientations. By analyzing these complex wave patterns, scientists can reconstruct the properties of black holes and neutron stars from billions of years ago. It's like deciphering an ancient language written in the ripples of space-time, revealing cosmic truths. Gravitational waves travel at the speed of light, making them the fastest carriers of information about these cosmic cataclysms. This allows astronomers to pinpoint the location of events almost instantaneously should a counterpart electromagnetic signal be present. This shared speed of light reinforces the fundamental connection between all forms of information traversing the universe, linking memories across vast distances. Future detectors, such as the Space-Based Laser Interferometer Space Antenna, or LISA, will operate in different frequency ranges, looking for gravitational waves generated by supermassive black hole mergers, or even lingering echoes from the very early universe. LISA promises to open up an even deeper window into spacetime's memory, detecting waves that have been propagating since the cosmos's infancy. Gravitational waves offer a unique opportunity to probe phenomena immediately surrounding black holes, regions where light cannot escape. By studying the ring-down phase of a merger, the final wobbles of the newly formed black hole, scientists can directly test Einstein's theory of general relativity under extreme conditions, peering into the dynamics of some of the most mysterious objects in the universe. The study of gravitational waves is still in its infancy, yet it has already revolutionized our understanding of violent cosmic events and the nature of spacetime. It offers unprecedented insights into phenomena previously undetectable, allowing us to reconstruct the cosmic history of black hole populations, neutron-star interactions, and potentially even the quantum mechanics of the Big Bang, pushing the limits of observation. Gravitational waves thus represent a new chapter in the universe's memory book. They are the silent, powerful whispers of massive bodies colliding across unimaginable distances and eons. They confirm that space is not an empty stage but an active participant, a dynamic medium that retains the echoes of its most dramatic events, offering a profound and fundamental record of the cosmos's turbulent history. Black holes, often seen as cosmic devourers, also function as incredible memory keepers within the universe. These enigmatic regions of spacetime are so dense that nothing, not even light, can escape their gravitational pull once past a critical boundary known as the event horizon. Yet, what happens beyond that horizon holds intriguing implications for the cosmic information paradox. The event horizon is the ultimate one-way membrane. It's the point of no return. Anything crossing it, whether matter, energy, or information, becomes inextricably bound to the black hole. This boundary is not a physical surface, but a region where the gravitational pull becomes infinite, marking the edge of a black hole's influence on observable spacetime, a definitive line of cosmic memory retention. Deep within a black hole lies the singularity, a point where matter is crushed to infinite density and space-time curvature becomes infinite. While we can never observe the singularity directly, its existence is implied by the theories of general relativity. It is the ultimate repository of everything that has fallen into the black hole, a place where all physical laws, as we know them, break down. The black hole information paradox is one of the greatest puzzles in modern physics. Quantum mechanics states that information can never be truly destroyed. But if something falls into a black hole, does it vanish forever? This conflict between quantum theory and general relativity suggests that black holes might either destroy information or somehow encode it on their event horizons. One proposed solution, the holographic principle, suggests that all the information about objects that fall into a black hole isn't lost but is somehow painted onto the two-dimensional surface of its event horizon, much like a hologram. This revolutionary idea implies that the universe itself might be a giant hologram, with all its three-dimensional information encoded on distant two-dimensional boundaries. Stephen Hawking's theory of Hawking radiation, while implying black holes slowly evaporate over cosmic timescales, further complicates the information paradox. If black holes radiate away their mass, what happens to the information that originally formed them? Scientists continue to debate whether this radiation carries the memory of the infalling matter or if the information is scrambled and lost forever. Stellar mass black holes are formed from the collapse of massive stars greater than roughly 20 times the mass of our Sun, after they exhaust their nuclear fuel and explode as supernovae. These black holes retain the ultimate memory of their parent stars, compressing enormous amounts of matter into an infinitesimally small volume, becoming incredibly dense cosmic remnants. Supermassive black holes, found at the centers of most galaxies, can contain millions or even billions of times the mass of our Sun. Their immense gravity plays a crucial role in galactic evolution, influencing the birth and death of stars and the overall structure of galaxies. They are immense gravitational anchors, holding the memory of countless stars and gas clouds that have spiraled into their depths over eons. As matter spirals towards a black hole, it forms a superheated accretion disk, glowing brilliantly in X-rays and gamma rays due to frictional heating. This disk is a vivid, dynamic memory of the black hole's ongoing feeding, a luminous record of the gas and dust being consumed. It tells us about the black hole's activity and its interaction with its immediate environment. Many active galactic nuclei launch powerful jets of plasma, traveling at nearly the speed of light, perpendicularly from their accretion disks. These jets extend thousands or even millions of light years into space, carrying energy and particles from the black hole's vicinity far into the galaxy and beyond. They are a profound memory of a black hole's energetic outbursts, shaping the cosmic environment. The debate over whether black holes truly destroy information touches upon the very foundations of quantum theory and general relativity. Until this paradox is resolved, whether through new physics or revolutionary insights, black holes remain the universe's most enigmatic memory banks, holding secrets that stretch the limits of our current understanding of information, space, and time. In a philosophical sense, everything that falls into a black hole contributes to its growth and its mass, thus leaving an imprint on its fundamental properties. While individual bits of information might be inaccessible from outside the event horizon, the black hole itself remembers the total energy and angular momentum of everything it has swallowed, altering its overall characteristics. Imagining what lies beyond a black hole's event horizon pushes the boundaries of human comprehension. While current physics suggests extreme curvature leading to a singularity, some speculative theories propose connections to other universes or dimensions. Regardless, the fact remains that whatever transcends that boundary leaves an undeniable imprint on the cosmic memory of existence. The interactions between supermassive black holes and their host galaxies are complex and profound. Black holes can regulate star formation within galaxies, either stifling it through powerful outflows or triggering bursts through gravitational perturbations. This dynamic interplay means that the entire history of a galaxy, its birth, growth, and evolution, is intimately linked to the memory held within its central black hole. Black holes, therefore, are not merely cosmic destroyers. They are also ultimate archives, silent, powerful repositories of immense cosmic history. They absorb and retain the memories of countless stars, gas clouds, and perhaps even smaller black holes, encoding them into their fundamental properties. They stand as enduring testaments to the universe's capacity to record and hold information in its most extreme forms. Beyond the spectacular events in extreme physics, the more mundane components of the universe also hold profound memories. Interstellar gas and dust clouds, the colossal cosmic reservoirs, are not just nurseries for stars. They are also vast archives of cosmic history, containing elements forged in ancient stars and nebulae that lived and died billions of years ago. Within these nebulae, gravity slowly draws together denser pockets of gas and dust. Over immense timescales, these clumps collapse under their own weight, forming protostars. This process is a continuous rewriting of cosmic memory as diffuse matter is condensed and reborn into new, luminous entities, carrying forward the atomic legacy of previous stellar generations. As a protostar grows, the surrounding gas and dust flattens into a swirling protoplanetary disk. This disk spins down and cools, becoming a dynamic memory of its parent star's formation. Within this disk, particles collide and stick together, eventually accumulating into planetesimals and then full-fledged planets. It's the blueprint for planetary systems. The process of accretion, where microscopic dust grains gradually build into planets, is a slow but steady accumulation of cosmic memory. Each planet, therefore, is a grand archive of the material from its nascent nebula. Its elemental composition, its isotopes, and its very structure tell a story of the specific conditions present in that stellar nursery billions of years ago. On Earth and other geologically active planets, layers of rock, sediment, and ice cores embody vast geological memories. Each stratum represents a different epoch, containing fossilized organisms, climate records, and evidence of ancient catastrophes like volcanic eruptions or asteroid impacts. These layers are a tangible, accessible memory of our planet's long and tumultuous past, stretching back billions of years. On celestial bodies without significant geological activity, like our Moon or Mercury, impact craters serve as direct and permanent records of their history. The size, distribution, and degradation of these craters tell tales of ancient bombardments, periods of intense cosmic violence, and the varying density of space debris over eons. Each crater is a scar, a memory of a collision. Meteorites, remnants of the early solar system, are literal time capsules. Unaltered for billions of years, they provide pristine samples of the material from which our sun and planets formed. Their chemical and isotopic composition offers profound insights into the conditions of the primordial solar nebula, preserving a direct memory of the birth of our own cosmic home. The chemical signatures present in stars, nebulas, and even exoplanet atmospheres are crucial forms of cosmic memory. Spectroscopic analysis reveals the elements present and their abundances, telling us about the history of nucleosynthesis, the creation of elements within previous generations of stars. This spectral data forms an eloquent chemical record of the universe's ongoing evolution. When massive stars end their lives in spectacular supernova explosions, they blast newly forged heavy elements like carbon, oxygen, iron, and even gold out into interstellar space. These elements enrich the surrounding gas and dust clouds, becoming the building blocks for subsequent generations of stars and planets. This cosmic recycling ensures the memory of stellar alchemy is perpetually carried forward. The entire universe is engaged in a continuous process of cosmic recycling. Matter from defunct stars forms new nebulae, which in turn form new stars and planetary systems. This cycle ensures that the elemental memory of past stellar life is never truly lost, but transformed and integrated into the next cosmic iteration, creating an unending chain of material history. Our own solar system formation is a prime example of this memory. The proportions of hydrogen and helium, the distribution of heavy elements, the specific orbits of the planets, all these features are a direct consequence of the conditions in the particular part of the Milky Way where our sun was born. Our very existence is a testament to the specific cosmic history that unfolded around us. On Earth, sedimentary rocks are particularly rich carriers of geological memory. Formed from layers of deposited particles like sand, mud, and organic matter, they capture environmental conditions, climatic shifts, and the living organisms present at the time of their formation. Each layer reads like a page in Earth's biography, revealing ancient landscapes and vanished ecosystems. Even ice cores, extracted from polar regions and glaciers, provide invaluable climatic and atmospheric memory. Trapped air bubbles reveal the composition of ancient atmospheres, while dust layers chronicle volcanic eruptions or meteor impacts. The thickness of annual ice layers speaks of precipitation rates spanning hundreds of thousands of years, offering a recent insight into Earth's memory. Asteroids, especially those from the asteroid belt, are often considered the leftovers from the solar system's formation. Their largely unaltered composition makes them pristine samples of the primordial material, preserving the chemical and physical conditions of the early solar nebula before the planets fully accreted. They are true, uncorrupted fragments of cosmic memory, from the grand scale of element formation in supernovae to the microscopic dust grains accreting into planets. The vast cosmos is ceaselessly writing its own intricate biography in material form. Every star, planet, rock, and atom carries a piece of this immense interconnected memory, waiting for us to decipher its story and unlock the secrets of its ancient origins. As conscious beings, humanity has also begun to leave its own indelible, albeit tiny, imprint in the cosmic memory. Our exploration, our artifacts, and even our unintentional debris orbiting Earth serve as monuments to our technological progress and our insatiable curiosity. We are not just observing the universe's memory. We are now actively contributing to it. Thousands of satellites, from communication networks to weather monitors, trace intricate paths around our planet. Each satellite, a complex piece of engineering, carries the memory of human innovation and intent. They are our eyes in the sky, our global connectors, collectively forming a burgeoning sphere of technological memory around our home world. However, not all our contributions are intentional. The vast amount of space debris, defunct satellites, spent rocket stages, and fragments from collisions constitutes a more chaotic and problematic layer of humanity's cosmic memory. This orbiting junk, from paint flecks to massive derelict components, stands as a record of our early, less responsible forays into the final frontier. Perhaps the most deliberate attempt to engrave a human memory onto the cosmos is the Voyager Golden Record. Carried aboard the Voyager 1 and Voyager 2 spacecraft, these phonograph records contain sounds and images selected to portray the diversity of life and culture on Earth. A message in a bottle cast into the interstellar ocean, meant for any intelligent life that might discover it eons from now. Preceding the Golden Records were the Pioneer plaques, carried by the Pioneer 10 and Pioneer 11 probes. These simple, etched aluminum plaques contain basic information about humanity and our solar system, including a diagram of our location relative to pulsars. They were humanity's first direct attempts to communicate our existence to hypothetical extraterrestrial intelligences, a very early form of cosmic message. On our own moon, the Apollo landing sites remain eerily preserved, undisturbed by weather or atmosphere. The bootprints of the astronauts, the American flags, the lunar roving vehicles, and scientific instruments. These artifacts are direct, tangible memories of humanity's historic ventures beyond Earth. They are silent museums on the lunar surface, frozen in time for potentially millions of years. On Mars, a growing collection of rovers and landers continues to explore the red planet's surface. From Sojourner to Perseverance, each machine leaves its unique tracks and samples, becoming part of Mars's geological and exploratory memory. These machines are our extensions, our robotic historians collecting data and leaving new scientific imprints on an alien world. The International Space Station, a marvel of international collaboration, is an orbiting home and laboratory for astronauts. Its continued presence in low Earth orbit, its daily passages overhead, signify a collective human endeavor to live and work in space. It is a dynamic, living memory of humanity's ongoing commitment to space exploration, a beacon of cooperation among nations. In the distant future, these human-made objects in space, satellites, landers, and even debris may become valuable archaeological sites for future civilizations, human or otherwise. They would tell tales of our technological infancy, our aspirations, and our early steps into the cosmos. They are artifacts, preserving the memory of a species reaching beyond its terrestrial cradle. The issue of space debris is a critical challenge, as it presents a threat to active satellites and future missions. Large amounts of junk could create a cascading effect, rendering certain orbits unusable. This growing problem is a sobering memory of the unintended consequences of human expansion, forcing us to consider the long-term impact of our actions on the cosmic environment. Beyond physical objects, humanity has also sent voices and radio signals out into space. Some of these are deliberate messages, like the Arecibo message beamed towards the M13 globular cluster. Others are the unintentional leakage of our television and radio broadcasts. These faint electromagnetic ripples carry the sounds of our civilization into the void, a collective memory echoing across the stars. Our expanding footprint into space, though microscopic on cosmic scales, represents a significant evolutionary step. From the first rockets to plans for lunar bases and Martian colonies, we are steadily broadening the scope of our immediate cosmic memory. Each new venture imprints a little more of humanity's story onto the grand cosmic narrative. The very act of striving for space, the creation of these cosmic memories, is driven by an inherent human curiosity. This quest for knowledge, this boundless desire to understand our place in the universe, is perhaps the deepest memory encoded within our species. It is this curiosity that perpetually adds new pages to the universe's ever-growing historical record. Whether through deliberate messages or accidental litter, humanity is undeniably leaving its mark on space. These traces, from the profound golden records to the mundane orbiting screwdriver, form a growing archaeological layer in the cosmos. They represent both our greatest achievements and our nascent struggles in becoming an interstellar species, a mixed legacy of human memory beyond Earth. Humanity's contribution to space's memory may be infinitesimally small compared to the eons of cosmic evolution, yet its significance is profound. It marks a species capable of self-reflection, of intentional archiving, and of reaching out into the unknown. We are a part of the universe that is now consciously adding to its own memory, a tiny yet vital chapter in the vast cosmic chronicle. The universe's expansion itself is a form of cosmic memory. The fact that galaxies are moving away from each other, and that this expansion is accelerating, is a direct consequence of the initial conditions of the Big Bang and the ongoing influence of dark energy. The scale and rate of this expansion encode fundamental information about the universe's past and its ultimate fate. The discovery of the expanding universe is largely attributed to Edwin Hubble in the 1920s. Observing the redshift of distant galaxies, he noticed that the farther a galaxy was, the faster it appeared to be receding from us. This groundbreaking observation provided the first empirical evidence that the universe was not static, but in a state of continuous, dynamic change, unfolding its past. Redshift, the phenomenon where light from distant galaxies appears stretched towards the red end of the spectrum, is a direct indicator of their recessional velocity. This stretching is due to the expansion of space itself, stretching the light waves as they travel. It's a cosmic odometer, recording the immense distances and times that light has traversed, a persistent memory of the universe's relentless stretching. Dark matter, an invisible and mysterious substance, plays a crucial role in forming the large-scale structures of the universe. Its gravitational pull congregated early matter into vast filaments and clusters, acting as a cosmic scaffolding. The distribution of dark matter throughout the universe today therefore holds a fundamental memory of the gravitational assembly process that shaped all galaxies. Dark energy, an even more enigmatic force, is responsible for the accelerating expansion of the universe. Discovered in the late 1990s, its pervasive influence acts as a cosmic anti-gravity, pushing galaxies farther apart at an increasing rate. The constant stretching of space by dark energy means that the universe is continually expanding its own volume, adding new spatial memory with every moment. The universe's large-scale structure is often described as a cosmic web, a vast network of interconnected filaments and clusters of galaxies separated by immense, relatively empty voids. This intricate structure is a direct result of early gravitational instabilities, amplified over billions of years. It represents the historical evolution of matter distribution, a large-scale memory of cosmic growth. Galaxies are not randomly distributed. They cluster along the pathways of this cosmic web, drawn by the gravitational influence inherent in the initial conditions of the universe. This clustering pattern is a persistent memory of the primordial density fluctuations that existed shortly after the Big Bang, dictating where matter would eventually accumulate and form stars. Superclusters, the largest known structures in the universe, are immense groupings of galaxy clusters bound together by gravity. These colossal structures, such as our own Laniakea supercluster, represent the culmination of billions of years of gravitational assembly. Their existence is a grand-scale memory of the universe's relentless drive towards forming larger and larger aggregations of matter. Each component of the cosmic web, from the smallest galaxy group to the largest supercluster, acts as a gravitational memory of the universe's past, Their motion, their shapes, and their relative positions are all influenced by the long-range gravitational forces that have acted upon them since the earliest epochs, subtly preserving the universe's ongoing history within its very geometry. The evolution of galaxies over billions of years, from irregular blobs of gas in the early universe to the majestic spirals and ellipticals we see today, is another facet of cosmic memory. Telescopic observations at different distances reveal galaxies at various stages of their development, providing a chronological progression of how galactic structures have changed and matured over cosmic time. By studying the expansion rate over cosmic history, cosmologists can reconstruct the universe's entire growth record. This involves analyzing redshift data from galaxies at varying distances, effectively mapping out how rapidly the universe expanded at different points in time. This cosmic expansion curve is a fundamental memory, illuminating our universe's past growth spurt and its accelerating future. The accelerating expansion, driven by dark energy, has profound implications for the universe's ultimate fate. It suggests a future where galaxies beyond our local group will eventually recede beyond our visible horizon, appearing as if they never existed. This future loss of observable connections offers a chilling reminder of how cosmic memory, while vast, might eventually become isolated for differing regions of space. The distribution of matter and energy throughout the universe today, its lumps and voids, its cosmic web, and the faint glow of the CMB, are all echoes of its earliest conditions. Every structure, every cluster, holds a gravitational memory of its primordial ancestors, tracing a direct lineage back to the initial, subtle inhomogeneities that set the stage for all cosmic complexity. Measuring the universe's past expansion rate is a relentless pursuit that refines our understanding of its entire life story. This involves precise observations of standard candles like distant supernovae and the analysis of baryon acoustic oscillations. Each new measurement adds another precise data point to the universe's historical record, making its memory sharper and more complete. The vastness of cosmic structure, seen through the lens of time, is a silent witness to the universe's ongoing evolution. From the subatomic particles to the superclusters of galaxies, every component plays its part in this grand, unfolding narrative. It is a testament to space's profound memory, continually accumulating and displaying its history across unimaginable scales. Beyond the observable artifacts and light-based memories, physics increasingly suggests that memory might exist at the most fundamental quantum level. The universe's quantum state itself could be seen as an ultimate memory, encoding all information about every particle and interaction that has ever occurred. This fundamental memory operates at scales beyond our immediate perception. Quantum entanglement, where two particles become intrinsically linked regardless of distance, suggests a form of non-local memory. Measuring the state of one entangled particle instantaneously reveals the state of its distant partner, as if they remember their shared origin and connection. This spooky action at a distance challenges our classical notions of locality and information transfer. The total information content of the universe, often debated in physics, is immense. From the positions and momenta of every particle to the state of every quantum field, it represents an unimaginable cosmic ledger. Whether this information is perfectly conserved and accessible or ultimately limited remains a profound question, but its existence points to an ultimate, all-encompassing memory. The James Webb Space Telescope continues to push the boundaries of what we can see, observing the universe in infrared light with unprecedented clarity. Its images of the earliest galaxies, of planets forming in distant nebulas, and of the atmospheres of exoplanets are constantly adding new, high-resolution pages to the universe's historical photo album, refining its memory like never before. Looking to the future, observatories like the Vera Rubin Observatory, previously known as LSST, will conduct vast surveys of the night sky, creating a dynamic, time-lapsed record of astronomical events. Such projects will capture changes in cosmic phenomena, from supernovae to asteroid movements, tracking the universe's memory and motion, building an unprecedented four-dimensional map of the cosmos. Future gravitational wave observatories, both ground-based and space-based, promise to unlock even deeper cosmic memories. They will detect the faint, primordial ripples from the Big Bang itself, the cosmic gravitational wave background, offering a direct probe of the universe's very first moments, a time before even the cosmic microwave background formed. The search for biosignatures in exoplanet atmospheres is another profound way to read the universe's memory. Discovering specific chemical combinations that indicate life could reveal whether biological echoes resonate across the cosmos, a memory of life, if it exists, beyond our own planet. It would be a groundbreaking expansion of what we consider cosmic history. The ongoing quest for cosmic knowledge exemplifies humanity's insatiable desire to read and interpret the universe's immense memory. Every scientific advancement, every collected photon, every detected ripple, expands our ability to decipher the grand narrative written in light, space, and time, perpetually adding to our collective understanding of our cosmic origins and trajectory. The universe hasn't stopped writing its story. Every moment, every stellar birth, every galactic collision, every expansion of spacetime adds another sentence to its immense cosmic autobiography. The memory it creates is not static, but continually expanding, dynamically evolving, ensuring that the cosmic chronicle remains perpetually open for discovery and interpretation. Humanity's role in this grand cosmic narrative is that of curious observers, persistent interrogators, and, increasingly, contributing participants. We are the conscious entities within this vast expanse capable of seeking out, interpreting, and even adding to the universe's memory. This unique position grants us a profound connection to the past, present, and future of the cosmos. The continuous unfolding of cosmic history means that memories are not only preserved from the past, but are also being continuously created in the present. Every new event, whether stellar, galactic, or even quantum mechanical, becomes a new entry in the universe's timeless ledger. This ongoing process affirms the universe as a living, dynamic, and ever-evolving archive. Every photon reaching our telescopes, every ripple of gravitational wave, every subatomic particle, and every atom carries within it an encoded piece of the past, a unique signature of its origin. They are the fundamental links connecting us directly to the cosmic moments that shape the universe and, by extension, ourselves. This profound connection is literally built on memory. The universe is not just an empty stage where events passively unfold. It is an active participant, a vast, dynamic information system. It records, retains, and presents its own history, constantly revealing new layers of its profound past. The concept of space having a memory transforms our view of the cosmos from a static void into a living, breathing historical archive. The profound implications of this cosmic memory extend beyond scientific understanding. They touch upon philosophical questions about time, causality, and our place in the grand scheme of existence. Knowing that every moment leaves an indelible imprint in the fabric of reality imbues the universe with a new layer of wonder and significance, turning it into a timeless story. We are living witnesses to this grand narrative, privileged to inhabit a universe that constantly reveals its past. Our ability to read its memories, though still nascent, deepens our connection to the Big Bang, to the first stars, and to the very elements that form us. It is a humbling and inspiring realization that we are a part of, and observers of, this magnificent, remembering cosmos. The journey of discovery is unending. As our technology advances and our theories evolve, we will undoubtedly uncover even more intricate ways in which space retains its memories. New particles, new forces, or even entirely new dimensions might hold yet undiscovered forms of information, waiting to be deciphered by future generations of cosmic explorers. Space truly has a memory, written in the light of ancient stars, in the ripples of spacetime, in the fabric of the cosmic microwave background, and even in the human artifacts we have sent beyond our planet. It is an immense, multi-layered archive, and we are only just beginning to learn how to read its full, profound story, piece by glorious piece. The silence of eternity, far from being empty, is filled with the echoes of creation, the whispers of colossal events, and the indelible imprints of everything that has ever transpired. The universe remembers, and in remembering, it invites us to remember with it, connecting us intimately to the 13.8 billion-year saga of cosmic existence